Hello everyone, this is my course project research on sentiment analysis of movie reviews on IMDB based on deep learning. I will present my research in 4 parts: introduction, data source and design, experimental results and analysis, conclusion. Sentiment analysis is a basic task in natural language processing, which aims to extract subjective emotion tendency from textual data. Traditional methods rely on manual features engine heavily, which face limitation in semantic expressiveness and computational efficiency. In recent years, deep learning techniques have significantly improved the performance of classification by automatically learning textual features. Data source: the study utilizes the IMDB dataset of 50,000 movie reviews, a benchmark dataset for binary sentiment classification, comprising 50,000 label reviews. Both is half of them is positive and half of them is negative. The dataset is partitioned into an 80% train set for model train and hypermeter tuning and a 20% test set to evaluate generalization performance. Experimental environment and processing: text clean, non-alphabetic characters were removed. Using regular expressions, retain only letters or and space, followed by low-case conversion, and tokenization and stop word remove. Text was split into tokens with white space and common stop words such as the and was flipped using NLTK's predefined list and lemmonization, sequence encoding, and padding. Model design and implementation: logistic regression model structure, input layer to linear combination layer to sigmoid function to output layer. Here is the code of logistic regression. Seeing model structure: input layer to embedding layer to this to global maxing point into designs to output layer. Here are codes of seeing model structure. The pictures are results of 2 models, and the table is their figures. Classification performance: the same model outperforms logistic regression across all metrics, which with the most significant improvement in recall. Feature energy: logistic regression relies on manually designed TF-IDF features, whose specialty might lose local semantic information in construct. The thing automatically learning dense vector representation through its embedding layer, effectively capturing word order and context relationship. Error analysis: mass classification samples by the thing primarily involves sacrum and complex negation structures, highlighting challenges in interpreting implicit sentiment. Comparison with cargo benchmark results: logistic regression average accuracy ranges between 88.2% to 89%, align with our result. Shallow neural networks average accuracy ranges from 89.1% to 89.5%. Baseline seeing models: on optimus, the scenes achieves 88.5% to 89.2% accuracy, while our scene models reaches the upper bound of this range. There are some limitations of this study. Feature dimensionality: limiting TF-IDF features to the top 5,000 terms might exclude high-frequency but crucial semantic signals. Model complexity: the scene's hierarchical structure improves performance but introduces higher parameter counts compared to logistic regression, raising overfitting risk in small-scale data scenarios, domain generalization. Both models required feature validation for cross-domain text adaptation. Potential improvements: architecture optimization. The integration of a tying mechanism such as transform or hybrid architectures or seeing LSTM enhances the capability to model long-range dependency, network deeps, stacking multi-convolutional layer with restore connection, multi-grass gradient vanish ensure and improves hierarchical feature learning, train acceleration, enabling GPU or TPU parallel computing, significantly reduce training time for larger scale data size. Finally, conclusion. Deep learning demonstrates significant technical advantages in test sentiment analysis. Its end-to-end automodel feature learning mechanisms. ELMET relies on minute feature analogy, while the synergistic interaction of convolutional carrier and embedding layers efficiently captures local semantic and contextual relationship. This approach offers a more flexible framework for modeling complex sentiment parameters despite remain challenges in interpreting implicit expressions such as sarcasm. The potential of deep learning in semantic abstraction and automated processing have been validated. That's all. Thanks for your listening.